I'm Larry Peterson, and I'm representing the Aether Project. Aether is open source, obviously. It is end-to-end. It's a 5G platform, and it's designed to run at the edge. So I'm going to give you a little bit of the history of Aether and talk about some of the components and what's going on right now. Is it's a new LF project. So just in way of background, Aether, if you take all the components of Aether and you put it together, you could call that private 5G. And that's not trying to imply the business model behind that. It just says that it now is available as an end-to-end platform you can run in enterprises, do local breakout, and deliver 5G service in an enterprise, whether that's offered by a telco or a third party or the enterprise itself is orthogonal to that. However, it is made up of a set of components, and those components could have been standalone open source projects in their own right. They're just part of this umbrella that we call Aether. Those two components, there's a cloud-native core, SD core, and a disaggregated software-defined RAN, SD-RAN, and I'll talk a little bit more about what goes into each of those in a minute. Just a little bit of the history behind the project. This started, I used the word incubated. This was built at the Open Networking Foundation, which, just show of hands, you've heard of ONF? So historically, this conference used to be ONS, Open Networking Summit. And ONF was a sister organization of the ONS. It was promoting software-defined networking, open flow standard originally, but it also started producing open source software. The Aether Project came out of that. It was a culmination of about 10 years worth of work with a sudden infusion of $30 million from the Department of Defense to build an open source, reliable, manageable 5G network. It had a lot of SDN components in it as well. So that's how it was incubated, and it actually then became an operational network. There was no SLA, there was no money changing hands, but the ONF staff ran and operated a service for a few years. And I just call attention to that because it's important that it's not just the individual components of the system, but it's all of the building infrastructure you need to run it to deploy it and operate it 24/7. Now, what has happened is the ONF has transitioned its projects to the Linux Foundation, including Aether. P4 was transitioned as well, and LF Broadband, which is actually a sponsor of this workshop, was also transitioned. There are 3 independent funded projects of the LF now as of February. So I'm just going to describe for you the reincarnation of Aether as an LF project in the rest of the talk. The biggest thing that happened is that we were transitioning from a model where if you wanted to be part of Aether, you'd bring up a site on the operational network. It was a managed cloud service. To you can bring up your own Aether now. So it's now a platform that is consumable by individuals, and I'll show you a range of ways that you can deploy Aether. So that's where most of the work has gone in the last several months is to help move that transition along. I said transitioned in the past tense. I would say it's probably true that it's still in progress, but we're getting close. So this is a busy space, and I wanted to give you a little bit of insight into the DNA of the project. First, it came out of an SDN organization that had been building disaggregated network services for a long time, and certainly a lot of that DNA exists here. But point one is that it's a combination of a lot of cloud technology. At no point in this did we attempt to build an OSS BSS in a traditional telco sense. We always tried to build the operational machinery around Aether as a cloud provider would do it. Okay, so that's the first critical point. And we use cloud native technology, Kubernetes, for example. So this was the history going back to NFV. This is not a VM-based solution. This is a Kubernetes-based solution. Now, you have to be careful with cloud native. Just because you use Kubernetes does not necessarily make it horizontally scalable and truly cloud native. But that is where we are going with Aether. And I'll come back to that in a little bit. It does have telco fingerprints all over it in the sense that we've attempted to stay 3GPP and ORAN compliant. So when there is a specification to adhere to that makes it, it's not play 5G, it's compliant with the standards. It still does that. Management machinery built around, again, is cloud-based. And finally, we were entirely focused on how to do this at the edge. So we've been deploying Aether with small cells, and there's local breakout, and it's an on-premise deployment of everything. You have the option of putting pieces back in the cloud, in a centralized cloud, but you are also able to put everything at the edge as well. Certainly the user plane stays at the edge. So Aether is kind of the intersection of those three spaces. We did not build it for telcos to deploy. There's a lot of technology that telcos could deploy, but that would require, of course, they bought into everything about the management machinery as well. So the components, I've already mentioned two of them. The key pieces are SD-RAN and SD-Core, and again, you could consume those as self-contained projects if you wanted to. But we deploy them on Kubernetes and a bunch of other tooling, the cloud-native tooling. We then have a runtime management plane, sometimes called AMP, the Aether management plane that runs on top of that. And there's a lifecycle management component. That's largely new because now we're trying to build it so that you could deploy it as opposed to our 3 engineers that happened to have built all of this in the first place, and they were the only ones that knew how to deploy it, and that's called OnRamp. So I'm going to talk about each one of those just briefly, just to give you a sense of what's under the covers. But before I get to that, just a little bit more of a background of where this originated. I said it was an operational deployment. As deployed originally, it had the management was all centralized, and then there were, I forget, a dozen sites worldwide that would run Aether clusters locally, do local breakout. We actually ran both the cloud management piece and the control plane of the core centrally. We had the user plane was all that ran locally in each enterprise. And again, that's sort of to say that there's a lot of cloud management machinery that's part of Aether. That's just built in, baked in. One of those sites happened to be Berlin, and you may have heard of, it's no longer operational as far as I know, the Berlin Open RAN trial that DT was largely behind. And Aether's subsystems were an integral part of that. Just wanted to call attention to that. All of this has been deployed in various settings in the Berlin trial, coupled up with all manner of independent components. So this was the first interoperable demonstration of Open RAN involving a lot of different pieces. We had XApps from different partners. We had radios from different partners and so on. And so it was, it's a 5G, the SD core, and the RAN is in there as well. You'll see SD Fabric as originally deployed. If you happen to know the history of Aether, it also had a cluster built using Tofino switches. What we're deploying now backs out of that, and we've just sort of that's an option, of course, if you wanted to do it, but we're not demanding that the software-defined fabric is a part of Aether today. It just makes it easier for people to consume. Okay, so now to dive down into the components just a little bit. SD Core was forked from free 5GC 5-6 years ago, so that was its origins, but it's been a long while. The 4G components were forked from OMEC, which was a Sprint and Intel project also, like from about a decade ago. So there's a lot of history here. What we ended up calling SD Core today has the option of both a 4G and a 5G control plane sharing a common user plane, common UPF function. And so it can be deployed in both ways. So if you go visit the SD Core website, you will find details on each one of the network functions and exactly where they are on the spec. In round numbers, it's release 17 of 3GPP. And this is not just a block diagram of functional building blocks. Each one of those then correspond to a Kubernetes pod. And so we'll get to scalability in a minute, but this is deployed as a Kubernetes workload. Same thing with the 4G, but I'm not going to pay much more attention to that going forward from here. The RAN, when I say RAN, it's dependent upon the disaggregated RU-DU-CU, and it's been used in combination with different examples of those components. But the primary piece that SD-RAN brings in as a software project is a near real-time RIC. And what we did, so you've heard about the ORAN open source version of this. This is a second open source implementation of the near real-time RIC. It was based upon, if you're familiar with the ONF's history of the ONOS SDN controller, that reached a point that it was re-architected into a set of microservices. Those microservices then were applicable to building a near real-time RIC as they had been in building, used in slightly different combinations to build wired SDN controllers. So there's a topology component that keeps track of all of the pieces of the RAN. There's a UE component and a config manager and so on. So again, I'm not showing that in quite the detail here, but there's a set of microservices for each one of those building blocks, and it also then runs as a Kubernetes workload. It supports the E2 interface and the A1 interface, and there's an example set of traffic engineering type load balancing XApps that go along with it. And just to complete the picture, it's at the moment not 100% compliant with the latest service models, but it has been, and we'll get back to the point that it's compliant with those service models. We sort of viewed this as an opportunity to be out in front of ORAN a little bit. It was never our intent to just follow along and say, what's the standard today, and then implement it. It was to say, how should this be implemented, and push that forward as to try to inform the service model definitions. But in any case, there is a now slightly out-of-date version of both of those, and they will be brought up to date. So, yeah, so that's the RAN component, the SD-RAN component. And again, they're both Kubernetes workloads. They both are independently deployable. The next piece I want to bring in is the management plane I mentioned. And this is where we start talking about end-to-end. You now have core and a RAN, and actually there could be multiple RANs here. I'll show you in a minute. But we have a runtime interface that is layered on top of that puts forward abstractions that might be meaningful to an enterprise. So enterprises are an abstraction. They get defined. They can define slices. They can define how different UEs map to different slices. They could assign QoS parameters to slices. They can map slices onto data planes, and sort of a whole range of abstractions defined on top of the config files that get dropped into the network functions, and presents then northbound a well-defined, I think of it as connectivity as a service API. And on top of that, then, you now are free to run closed-loop control programs, which was kind of the intent of the original Aether project to start with, is to demonstrate how to do closed-loop control. Yeah, so all manner of data collected and all manner of control operations that you can turn around and apply, and the management layer then will cause the right changes to be made on the underlying subsystems, whichever might be the appropriate one. An example of that, which I'll just mention briefly a little bit later, but just to put it in here as a placeholder, there is now a new project. This has not come out of this is not the original Aether, but now something that's happened in the last few months called Smart 5G, which is basically an effort to collect data and use ML to do closed loop control on the power being consumed by the underlying RAN. It's the FCC funded, which department is it? Commerce. The Department of Commerce funding of this work. All right, so I'm not going to go into the details of this, except the point being that there is a control API, a well-defined control API. Now turning my attention for a few minutes to what mostly has been happening, if you'd followed Aether before, that's now different. And maybe once before you tried to install Aether and you couldn't because it was just too hard. What we've been basically focusing on the last few months is trying to make Aether more easily consumable. And to make it more consumable, in essence, we're tackling exactly the problem that everyone's talking about at this conference, which is how do I give operators, and it may be an enterprise, it may be a telco, the wherewithal to set up and manage a system like this. Obviously, that's not a terribly easy thing to do. And our general strategy here, well, let me walk through a couple of slides, and then I'll get to the philosophy of how we went about doing this. So we had already a fairly complete CI/CD pipeline. It's just that it had been one that produced deployments that we pushed out continuously to the deployment of Aether, because we had an operational cloud. And it was built out of just a whole collection of open source projects. In particular, if you're over towards the right end, Rancher and Terraform were key components of the way that we did the deployment in the original implementation. What we have attempted to do is stand back and say, and the truth is, if you wanted to deploy this, then that the ops team was a set of people who had put all of this infrastructure together, and they were the only ones that knew how to make it work. I mean, that's just the way these systems end up. So we wanted to lower the barrier to entry there, and we wanted anyone to be able to pick up this code and deploy it. Now, maybe you do development as well, and maybe you push through changes, and we need to make it easy for you to do that. But assuming that you're just going to take the artifacts that our CI system produces, the Docker containers and the Helm charts, you ought to have the wherewithal to do that. And so, yeah, we don't technically call it my Aether, but that's just to give you a sense of now you can deploy Aether and you can operate it. So one of the key things that we did was we needed a lower entry point, an on-ramp, which is where that name came from, to that deployment. And what we ended up with there was we went with Ansible, and there's some different reasons for that, but what I ended up liking, this was a little bit new to me, so I knew of Ansible but had never actually used it, is it does have a pretty low barrier to entry, and it can ramp up to more and more sophisticated deployments. And so that seemed like a pretty good starting point, and I'm pretty happy with how that ended up. Hearing about the new project here, Nefio, there's some similarities. We ended up using a lot of what they would use for the spec for how to do the deployment for us turns out to be Ansible variables, and we've just extracted the variables that are most likely you're going to need to change up into a central place, and that kind of localizes where you have to think and apply your local information to it. But it's a similar idea in spirit, and collectively then that thing is called Aether OnRamp. And what it does is, this is where I wanted to get into the philosophy of a little bit. The goal was to help the user own the issue. So, and this is, I mean, why not just take a little step back from what's going on right now? A lot of the times when you see some solution that's going to make it easy for you to do something, what that says is we will hide all the magic and you just give us the 6 parameters we need and we'll go do it. And that's a great, simple thing to do, except after having done that, you don't know what just happened. And you're entirely dependent upon that magic continuing to be magic for you. And there are some really good systems built. This is actually absolutely not a judgment on the Nefio thing. I actually think it's pretty cool. But what we discovered was that we had to expose the magic to you along the way. Otherwise, you would reach a plateau and there was only so far you could go. Now, occasionally this will frustrate the really, really savvy engineer who knows everything, and then they will find this a little bit too cumbersome, I guess you could say, to follow the slower on-ramp. But from the point of view of getting people to adopt Aether, it was really important that we do have this less steep learning curve. And the way that OnRamp is built actually exposes you to every little incremental thing that you then gives you ownership of it. And now you can go do it yourself, and you can now modify it in whatever ways you want to. So it's designed to scale from something very simple. A student could pick this up and run it on their laptop in a VM. You could go get a VM on Amazon or wherever, your own local cloud, and you can deploy this in a single server. You can ramp up, you can scale up the number of servers. You can connect physical or virtual emulated RANs to it, Gnode Bs. And so all of those combinations are now available to you depending on, your starting point is called the quick start. So we define blueprints, and then you start with probably the quick start blueprint, it's the easy one. And you can, again, ramp it up to eventually multiple sites. And in the transition, we've now got it very solidly working for one site. And so the next step is, can you bring it up in multiple sites? And that the machinery is sufficient, we just haven't taken that step just yet. So just to give you a sense of what these blueprints are, quick start blueprint basically brings everything up in one VM. Now, when I say everything, it starts out with the core. That's kind of the central piece that's always there. The RAN is what changes a lot of the time. So in this particular diagram, you've got the Kubernetes core, and in the corner there with the dotted edges around it is the G-Node-B simulator. So it is an open source simulator that puts a lot of pressure on the SD core control plane, not so much the user plane. It's not a throughput test, but it's a latency test on the control plane. And you can now bring it up and watch packets fly and do packet captures and look at the logs and understand how everything's working. And that's actually then, if you make changes, it's the first test that you run. You can also then take the G-Node-B sim out of the server that is hosting Aether and scale it up independently. This is really important that you could get the workload separated from the cluster. And the workload now scales. So you can have multiple VM/servers. I've shown 2 here, and you can have multiple containers per. So you can really scale up the user plane, the workload generation if you want to. Meanwhile, what was running on a single node Kubernetes cluster before is now running on you can scale up the cluster. And this is a trivial thing to do in Ansible, and how you control the nodes that things get deployed on. And so now, from a blueprint point of view, the blueprint includes the host inventory file that basically you edit to match whatever it is, whatever scalability you wanted out of the system. That's the emulated RAN. It also then, we work with Moza Labs, which is a US private enterprise-focused subsidiary of Seracom, who produces small cells. So we've been using those small cells, and we have a bunch of them around the country with different labs bringing up Aether using live small cells. And as I mentioned before, SD-RAN now, the disaggregated software-based RAN is also an option to run as a RAN. And when you run it's also running in Kubernetes. And I need a pointer over here. So we've got, what did I have? I've got ONOS topology and ONOS config. Those are 2 of the microservices that implement the near real-time RIC. In this particular case, instead of an external radio, we booted it up with RAN-Sim, which is yet another simulator that we have. It simulates a RAN. And so that's sort of the default first step version of getting you both SD-RAN and SD-Core running together. And that we will embellish and turn into more complicated blueprints over time. So those are all example blueprints, just to give you an example of the way the blueprints scale up in servers, scale up in functionality, and how you take ownership of doing that. So for the last few minutes, I wanted to come back to a couple of new things that have happened or are now happening. And these are uses of Aether, not commercial deployments. There are a couple of things going on there, field trial deployments. I'm not going to talk about those, but these are how Aether is being used and then improved. And the first one is how to scale the core. And the issue here is scaling the control plane of the core, not scaling the user plane. Scaling the user plane is pretty easy. It's scaling the control plane that's difficult. And why would you want to do that? Because if you connect a 5G core to a set of IoT devices, they are going on and off and silent most of the time, constantly. And it's entirely about the latency of the control plane in servicing these scalable number of IoT devices. So you might have thought it was already scalable. I've drawn little Kubernetes pods there. Why don't you just add to those pods? Well, easier said than done. So as far as we know, and I'll have Shabazz, who is behind the research that I'm describing here. I'll credit you in just a second on my slide. As far as we know, anyone that's attempted to take a 5G core, and the whole point of one of the important points of 5G was that it could be cloudified and cloud native, and you can draw those pictures pretty easily, but actually making that horizontally scalable is extremely hard. It's so hard that every example that we know of basically gave up and collected everything together into one giant blob of code, which is exactly the opposite of disaggregating these components into their individual microservices. So and the reason it's hard, or one reason it's hard, is because this is not a typical web server workload. We've got packets going in both directions. There's actually state that has to be maintained. And so if you wanted to be true to the microservice architecture and the cloud native design, and yet get cloud native scalability out of it, you have to work really hard. And Shabazz and his student, Blah, worked really hard. And they've been able to retain the flexibility of the microservice architecture. They've been able to get scalability, and they've been able to get low latency out of it at the same time. And so I just cut a couple slides out of their paper just to give you a little bit of a flavor of it. And Tegra is what they call the resulting system. I tend to think of it as Aether next version, because they're going to fold the results back into the deployment. That hasn't happened yet. It'll happen this summer. And the next time you pick up the next release of Aether, it will have the scalability features in it. But the thing to note, so Tegra with one server is exactly Aether, because Aether didn't scale by itself. Tegra with two is 2 servers, 3 servers, 4 servers, or 4 growing the pods. So the first thing to notice is that when you went from even just 1, I can't see the number of minutes. Thank you. I had minutes left. So the penalty that Tegra introduces is the difference between the first and the second column in each one of those as you increase the workload is extremely small. There's not a lot of overhead being added. And of course, as you scale up the number of UEs, the latency goes up, except the more capacity resources you throw out, the latency goes down. So that's just the general shape of the curve. But I wanted to draw your attention to the last column, which is the first, the 25K. That's basically, instead of just pounding workload at it as fast as possible, it used a trace of real workloads. And so it's spacing out the requests. And this is entirely for registration events. There were other measurements for other events. But basically, you can see the kind of speed up you get as you add resources. It's substantial. And the latency is good to start out with. And that then shows up when you look at the scalability graphs. The red is just plain old Aether, and as you add workload, the latencies grow and eventually top out. But as the blue line is the Tegra, as you add instances of both the SMF and the AMF across time, and I'm not going to go through the details of why that looks just like it does, it does stay pretty flat and scales linearly. So that is a fantastic result, due entirely to their hard work, but this is something that will get folded back into Aether really soon. The last thing I wanted to say is, so it's Smart 5G, and basically you can take Aether, and because of the interfaces and APIs on top of it, you can start collecting data about power usage and data usage. And what we're going to build, what Smart 5G is going to build out of that is improved APIs. That's basically the work product here, is some better APIs, so that they can then do closed loop control and do power management. And ultimately, if you can learn about the traffic, you can predict what is going to happen. And at that point, have an opportunity to shut down cells, power down cells, whatever adaptions you want, pretty quickly. So there's more about this online. So let me just actually get to the final slide, which is just a little bit more information. If you have questions about Aether, we're still in the process of transitioning to LF, so not everything is done. The web page, if you go to that web page, you'll get the old ONF web page. That's fine. We'll get it moved eventually. There is now a wiki. There is a pretty complete guide that helps you bring up Aether on your own. And all the source code is on GitHub, except it's a little weird where to find it because it's under organizations that existed a long time ago with funny names. So with that, I will stop, and I think there's time for a couple questions.